welcome everyone who is watching the live stream, especially if you are in the AP region where it's already late night. So thank you for joining everyone. My name is Csaba Fitzl, and I will talk about exploiting directory permissions on Macos. A few words about myself. I recently joined Offensive Security as a content developer to write trainings. I used to be a red teamer and a blue teamer before that for about 8 years. And recently I started to do plenty of macOS research, and this talk is also born out of that. I have a wife, 2 kids. We love to do hiking, especially in the Alps when we get a chance to get there. And I also do yoga. So let's start. The agenda for today or for the talk is, first, I will talk about the macOS file system permission model and all the nuances around that. Then I will talk about how to find these bugs that I will talk about. Then I will cover plenty of bugs related to these, and at the end I will also briefly mention how to prevent these kind of attacks. So the first part, which will be the macOS file system permission model, which is very important to understand so we can actually find these bugs. The first entry is, so macOS is based on FreeBSD, or at least it complies with the BSD, and so it applies and has the classic POSIX security model for the file system. So if you are familiar with any Unix, Linux system or macOS itself, the POSIX model is really the base of the entire system. And this means that every file and directory on the system has 3 sets of permissions. One is for the owner of that file or directory, which is really the user. Then we have a group owner permission. And then we have a third one, which is for everyone else. It's also called the word permissions. Now, each of these entities can have 3 different permissions, which are read, write, and execute. In case of files, the read, write, and execute permissions are kind of straightforward. So if you have a read access to a file, then you can read the file. If you have write permission to a file, you can write to it. And if you have execute, then if it's an executable, you can execute that file. Now, in case of directories, this is not that straightforward, or at least it's not that self-explanatory. In case of read access to a directory means that you can enumerate the entries in the directory. So like if you do an ls and you list the files, you need read access for that. In case of write access, it means that you can delete and write files to the given directory. And in case of execute, that means that you can traverse the directory. Now, if you don't have execute permission on a directory, it means that you can't access any files inside that or any of its subdirectories. And not being able to access means that you cannot even list them. So if we go into some of the scenarios with some corner cases, so let's say you have read-only writes to a directory. That means that you can't access any files. Even though you have like list or enumeration access, you still can't list those because you don't have execute permissions. So having just read-only permission on directory, it's not really useful. Now, having execute only, you still can't list the files. So if you do an ls, you will not see anything. But if you know the file name, you can access that file by its name because you can traverse the directory. Now, obviously, if you have access to the file itself. But basically, this is how directory permissions can limit your access to files. Now, if we do a simple experiment, which you can also try. So let's create a directory, call it whatever you want. I called it restricted, and create a file inside it. I created AAA, and I put AAA into the file called AAA. Now give 777 permission to AAA, which means that everyone, the owner, the group, and everyone else will have read, write, execute to the file. So for sure, you can access that file. And to verify it, you can print out the contents, and we can see that we can see the contents of the file. Now, if you change the permissions of the restricted directory to 666, which means you basically only give read, write permissions to everyone, like the user, the group, and everyone. Then if you try to print out the contents of AAA, you will get an access denied. Now, if you try to list the directory, you will not see anything, although you have read access. And again, you can just verify that indeed it's only read, write access on the directory. You can try to list that file, but again, you get permission denied. Or if you just, Now, if you change back the directory rights to 755, so you give everyone read, execute permission, you can list again the files, and you can see that our file is there. Now, two interesting scenarios which can lead to a potential bug or some exploits. One is that, let's say you don't have execute permission on a given directory, but there is a file inside to which you would have access based on the file permissions. But you cannot access it because of the directory limits you. But potentially there is a way to leak out that file from that directory outside, and then you will be able to read that file. We will see about for this kind of leaks. Now, there is a more broader one, which probably 90% of the bugs I will talk about. If you have read, write access on a directory, or read, write, execute, so you can delete, create files. You can delete and create files regardless of the permission. So let's say there is a file owned by root in a directory where you have write access. You can delete that file. Now, I think that's not intuitive, because you would expect that, okay, if the file is owned by root and no one else has access to the file, you can't touch it. But that's not true if you have write access to the directory. You can delete it and then create other files. So this is the main scenario that we will exploit in the upcoming cases. Now, a few other, so this is a base case, the POSIX model, but there are many other modifiers to the permission model, and one of them is flag modifiers. There are many flags. I will not cover all of them. There are two which are important from an exploitation perspective. One is the uChange, UCHG, or uImmutable. They are all the same, but just different names. That means that no one can change the file until that flag is removed, even root. Now, a root can remove the flag and then delete the file, but by default, until the flag is there, you cannot do that. So if there is a file owned by root and it has the uChange flag, you can delete it. You cannot delete it even if you have write access to the given directory. And there is another one which is macOS specific. It's the restricted. It basically means that it's protected by SIP, System Integrity Protection, which basically means not even root can modify those files. They are write protected. This is typically the core system files, core system binaries. And you basically, if you want to touch those, you need a special Apple entitlement for that, which of course you will never get. If you list the root folder on macOS, you can do ls-l capital O. You will see all of these flags. There is a couple of restricted, which means that it's protected by zip, as said. There are a couple of folders or directories seen as hidden. It means that it's hidden from Finder by default. You can still list them on Finder, but by default, you will not see all of these directories. Now, there is another important modifier. It's called a sticky bit on directories. And it means that the file system will treat those files in such directories in a special way. So only root, the directory owner, or the file owner can rename or delete these files. This is typically applied for temp directories. And it basically involves that everyone on macOS or Linux has write access to temp folder. So you can write your own files there. But because of this sticky bit, let's say I'm putting there my files and John is putting there his own files. I cannot delete his files because I'm not the owner of the directory and the files, and I'm not root. Additional temp is usually owned by root, so it's really only the root and the owner who can change those files, which basically means if there is a file in the temp folder, you cannot delete it if it's owned by someone else. So this is like another exception for our case before, when you owned, you had write access to the directory, but you could still delete files which were owned by root. In case the sticky bit is set, you cannot do that. Now there is another control because the POSIX model is not granular enough, so you cannot really do unique permissions per user. So there are access control lists you can attach to files with plenty of access control entries, and it can be applied to multiple users groups. So you can do individual user rights or group rights for files and directories for file, and even the permissioners are broader than the standard read, write, execute. For example, for files you have additional append rights, and for directories you have a search, add file, add subdirectory, delete child, and so on. Although this model exists, I haven't seen it widely used. It's being used to some extent, but it's not that widely used on the system. So it's not that significant from our perspective, but still worth mentioning. What is significant is the sandbox. So SIP is also being enforced by the sandbox. SIP is basically the platform profile on the system, and it's just being applied to everything. And it can further restrict file access. Typically, it's done through the sandbox profiles. Now, most of the daemons that run as root on the system, we have a predefined sandbox profile. These can be usually found in the USR share sandbox or the system library sandbox profiles directories. These are SB files and containing plenty of rules what the process can or cannot do. They are written in SBPL language, and I will not go into the details how it's formed, but this is one example on the screen for such a profile. It's for the MDS daemon. I think even if you don't know that language, you can still read these rules. So for example, there is an allow 5 write, which means that you have 5 write access. And there are literals, which means like exact location. In case of files, you can do reject, subpass, and so on. There are basically allow and deny rules, and not just for file read writes, but also many other things. So even if you run as root as a daemon, you are limited by this profile. So even if you would have by your user ID access somewhere, if your sandbox limits you, you cannot write there. So that was the theory. Let's go and find some bugs. I think they are not so hard to find these bugs. I found two methods to be pretty fruitful. One is a static and one is a dynamic method for this. The static method basically involves you analyze the current permissions set for directories and files, and you try to find these interesting combinations by just basically crawling through the file system and checking for permissions. Which we will mostly use here in the following sections is typically if the file owner is root, but the directory owner is different. So which usually means that you have usually some sort of write access to that directory. Now, another interesting case could be when the file owner is not root, so it's owned by like a regular user, but the directory owner is root. That would mean if no one else has access to the directory, that file is being touched by a process that is running as root, but you have write access to the file because you are the owner, then there is a chance that you can mess with that process that runs as root. The third case is kind of similar to the first one, but it's more broader. So the file owner is root, and basically through one of your group membership, you have write access to the directory. But maybe you are not the owner of the directory. Maybe it's owned by root, but maybe the admin group has write access to the directory. And there is a fourth case. I also found one use case for it. It wasn't that significant, but still worth mentioning. When the file owner is not root, but the group is wheel. Wheel is really the group where root belongs to. And then the parent folder is also not root owned, so you likely can do something with that file and maybe gain access to the wheel group. It's not so significant, but could be still interesting. I have a Python script scanning for this combination. It's up on my blog post, basically, where all this is discussed. Now, there is a dynamic method. Basically, you can monitor for this relationship dynamically. So every file, write or read, you can monitor, and you can check for these the previous combinations in terms of the process, is it running as root, and if you as a user has write access to that file. Now, most of the time you will find the same stuff as with the static method, but where you could find more interesting items is two cases, basically, when the root process will change the file owner to a regular user, which means that just scanning through with the previous method, you will not find it because the file is not owned by root, but it was touched by a process that is running as root. And also, if the process is just reading from the file as a root process, but you are the owner of the file, maybe then if it's a configuration or something, then there is a chance you can affect that process that runs as root. So let's talk about the actual bugs. So again, the general idea is that we want to redirect the file operation to a location we want. And the typical process is we delete the file because we can do it. We have access to the folder, to the directory. You place a symlink or hard link to that file, and you wait for the process that runs as root and do something with that file, and hopefully you can redirect the write operation. In some cases not. But so there are a few problems that you can run into, which can lead to an unexploitable scenario. The first one is that the process might run as root, but because of sandboxing, it might not be able to write to any interesting location. So in that case, we don't really have a bug, although you could redirect it to somewhere, but if there is nothing really, or it's limited to one file only maybe, then it's nothing major there, maybe not even a bug. And now there is another case when the process will actually not follow the symlink or hardlink you put there. It will simply overwrite it. And I found many cases for this. And I will talk about at the end when this happens. So it will just overwrite your link, you create it there, and that's it. So you cannot exploit it. The third part is you successfully redirected the file operation, but the file that was written out is still owned by root. So it means that you still cannot modify it, although you could write somewhere, but it's the same content as it was before. So we need to find a way to affect the contents of that file to our benefits, which might be possible, might not be possible. And actually, in most cases, it's not possible, but in some cases it is. And then it's very interesting. So again, in case 1 or 2, we don't really have a bug. And yeah, you want to control the content. Or there is another case, let's say it's a configuration file that you can touch. Then there is a potential you can affect the configuration of a given process that is running as root, and that could give you something interesting. So the first bug I will talk about is the install history plist file. It was a simple arbitrary overwrite on macOS. Whenever anyone installs an application, a log will be created in the install history plist file, which is located in library receipts. You have access to that. You have write access to the directory as an admin. You can delete the file, place symlink. It will be followed. You can do overwrite files basically, but unfortunately, the content, as you can see on the screen, it's an XML file with the date, the name of the application, package identifier, and so on. So you can't really do too much about this unless you poke around the metadata of the application, but nothing beyond that. You can trigger this by basically install something, either from the App Store or from a package. The next one was an Adobe Reader installer vulnerability. Again, this will be only an arbitrary file overwrite. At the end of the installation of Acrobat Reader, there was a file placed in the temp directory with a static name. Now, if prior the installation, you create a symlink to this file. So this file doesn't exist before installation. So you can create a symlink, and once the installer is done, it will follow that, and you can overwrite basically anything. It has a fixed content, so again, nothing major here. Now the following one was more interesting bug. This is again something for macOS. There is a diagnostic messages history plist file in the library application support crash reporter directory with read permission. Now you can again place a symlink to this, delete this file and place a symlink somewhere. And what happens, there will be no overwrite happening. But if you point that symlink to a plist file, then the file permissions, the target file permissions will be changed to read, write, which means you can grant Word read access to any plist file on the system, and you can grant group write access to any plist files on the system. the owner and the group of the file will not be changed. So it will remain whatever it was originally, but you can still potentially extend permissions. Especially you will grant really global read access to these plist file, which are typically configuration files. You can trigger this bug by going to the analytics and improvement settings on privacy and clicking around the settings. And if you modify these settings, then this file will be touched. And you can look for interesting plist files. There are two on the screen, which normally only root has read access, but by redirecting this operation, you can grant global read access to these files, and you can check their contents. But again, overwrite will not happen, but you can get new permissions. The next one is file disclosure vulnerability on Macos involving the font mover process. So the library fonts directory on Macos has a group write permission set for the admin user. So this means if you are in the admin group, which like regular users, if you run Macos in a single user mode, you can drop the files. This folder is really containing the system-wide fonts on the system, and we will see, but I think this privilege for the admin user is really not necessary in this case. So how the exploitation happens? So you download the font, any font really, you double click it, and the font wizard or whatever will come up. And before you move on, you need to set the install location to computer instead of the user. Now, in case of the user, it would go to your home folder to library fonts. In case of computer, if you go to the library fonts directory, what I just mentioned before. So you press install font, install ticked. You will get an authentication prompt to root in case of the computer, and then the file will be copied over. Now, this is why I said that I think the admin user shouldn't have write access to this location, because you will get the root prompt anyway. And if you will force to authenticate for the process, it's pointless to maintain that permission. But so what I tried first is I can place a symlink or hard link into the library fonts folder, but they will be removed. You can, I never could win the race condition. And even if it worked, font mover is sandboxed. So if you check the font mover sandbox profile, it can only really write to library fonts, which is kind of the same place where you already have write access. But the file disclosure vulnerability happens with regards of the source file. So when you do the, I will go back. So when you do the install font here, sorry, and you get this screen, at this point, you can swap the source file, the font you are trying to install. And if you place a symlink there for the source file, font mover will follow it and read out that file from whatever it is and place it to the library fonts folder directory. And it will maintain the original permission of the file that it moves. So at first sight, this is not really interesting because the file is being moved to a location where what you already control, and the file permissions are unchanged. So like if you didn't have read access to it before, you will not get read access to it. But there was this POSIX corner case in case you had user or everyone, or so you had read access to the file, but you didn't have execute permission on a directory where this file lives, then you never could read this file. Now with this process, basically you can leak out this file to a location where you have directory execute permissions, and then you can read this file. So it's kind of limited. And again, it's a corner case of all these permissions. But potentially, again, you can leak out files and read files that you could never do before, and maybe you can find some tokens or passwords or some interesting data that you can leak this way. Yeah, exploitation is what I mentioned before. Before you click install ticked, you can replace the file, and then you can read the file, whatever you copied. The fix was basically they verified their file replacement. So if you messed around with the file during this process, the link will not be followed. So you can't copy out files from a custom location. Next one is again just a file overwrite vulnerability, but it will be interesting because we can control the content to some extent. So it's the usual story on the private var log diagnostic messages. Directory is writable, and there are a bunch of ASL log files, and you can exploit them through hard links. And actually, when you put your hard link there, you might need to reboot the system, so it will actually use that hard link. But again, it's the standard story with the redirection. Now, this is the log file. So there is a potential that we can control the content, and yes, we can, but unfortunately only partially. These are ASL logs. ASL is, I think, the Apple system log. It's a very old API. I believe it might be even getting deprecated these days. There are very few documentation around it. And if you check around the private var log location, there are many ASL log files. So this is not the only one. And it's kind of, I couldn't figure out how you end up in one ASL log bucket versus the other. And also, if you look on these specific ASL logs on the diagnostic messages folder, then it seems like a sort of predefined logs with some data or with some fields and with some data around it. So I never saw like any custom string, but I kept looking, and I finally actually did found one log which contained like a string and not a predefined field in the log, which was the CalDev account refresh completed. Searching for this text, it led me to the calendar persistent private framework. And if we reverse engineer that framework, there is a stand statistics function, and it will call the call message tracer object or class as log function. Sorry, the call message tracer log, and you can see that the CalDev account refresh completed is a custom string coming from this location. So let's follow the call message tracer that leads us to calendar foundation. And if we check the call message tracer function, I used Hopper for reversing it, we can see that indeed it is using the ASL API. And if you start to reverse, okay, if I have a custom message coming, then how should I end up in that diagnostic messages log bucket? But it started to be really complicated, and I just stopped reversing at that point, because we already have a function which, if we provide it with a custom string, it will log for us in the diagnostic messages log file. So basically, we need to import the calendar foundation dylib. We need to load it. We need to look up the class, the call message tracer, and we can invoke its function. Patrick Fardell has a really nice post around reversing PKG util, and he walks through how to use private APIs, how to import those API, how to look up classes, and how to use their methods, basically. So I just followed that, and basically it was a really short script to send logs to this bucket. And I could insert a custom string, whatever I wanted, into the log file. Now, unfortunately, the way the entire log file is set up, even if you delete it and start from scratch, so you send in you will be the one who is sending in the very first log file. You cannot really use it for code execution because of the file header and so on. But I think it can be still a useful trick to reversing private APIs and somehow partially controlling content. The next bug is Adobe Reader macOS installer. This was actually a full privilege escalation. It was in the Acrobat Update Helper app component. There is a directory created in the temp folder during the installation. Of course, it will be owned by root. But there are two plist files in this directory structure that at the end of the installation will be moved into the library launch daemon folders. These files, again, are on fixed location. And the issue was that, okay, I created the directory and everything before the installation in the hope that, okay, the installer will move my files. But unfortunately, the installer deletes if there is an existing folder with that name. But you can do a race condition, so you can recreate this directory structure after the deletion and before the installer creates. And actually, it's pretty easy to win this race condition. So you start the installer, start the race, and if you can create the directory structure, it means that you own it, and you can place there your own plist file that will be moved at the end to the launch daemon folder, which means that you will gain root access because if you can place a plist file in the launch daemon, then it means that that plist will be executed upon boot, or not the plist, but the command you put into the plist will be executed as root upon next reboot. Now, the last bug to cover is the done with the macOS periodic scripts through mon pages. So what happened? So macOS has a few maintenance scripts. Their respective launch daemons can be found in the system library launch daemon directory. There is a daily, monthly, and weekly plist pointing to various scripts, and one of the weekly scripts is the what is script, which basically rebuilds the man page database, and it will run it as root. It will get the mon page paths and reconstruct the database. Now, if you ever installed brew on a Mac OS, the USR local share man folder will exist, and it will be owned by your user ID. I think it doesn't exist by default. only if you install brew, which I believe most IT people will do. So the make what is script will create a whatis.temp file, and you can redirect it through a symlink. And our target will be launch daemon folder, what we used before with the Adobe bug. And now the problem is that the plist file has to be a proper XML file. If it's not a proper XML file, the plist will be ignored and it will not be run. Now, if we check the what is database, which is on the screen right now, you can see that these are name and description separated with dashes. So it's not really an XML file. Now, the left part of the database is derived from the file name of the man page file. And the second column is taken from the name, basically the entire name section of the man file. So how do we get an XML from this? The first step, we take the man page file, go to the name section, and the second part, and basically the string, the long string that would be the description for the man page, we put our XML there. We put our entire plist file in a one line. And we put a start of comment at the very end, because this will be one of the man pages, and there will be many others. We want to comment out everything else that comes after this, and then it will be a valid XML file. We have our plist, which is also a valid XML file. We just need to take care of the first part now. Now, the second, step 2, okay, I will skip this. So the file name, because that controls the first column on the man page database, it has to make sense in XML. Now, interestingly, the thing you see on the screen, the brackets, exclamation mark, dash, dash, and whatever thing, this is a valid file name. So you can give this name to a file on Macos, and I believe also on other Unix or Linux system. And this is a valid XML string. It's a start of comment again, which is good. But we need to go back to our first step, to our man page, and we need to close this comment so it will not comment out our entire plist. So before our plist starts, the actual XML, we close the comment. So what we get at the end, this comes from the man page database. It will be the first line. Because of our special characters we use for the file name, it will actually go to the top. For any case it doesn't, just rename the other files that come first, so they are degraded, or they will come later in the alphabet. And basically you can see that we managed to construct a valid XML based on the man page name section and the file name. And we can create our symlink now, and you can simulate running the weekly script, or you can wait a week when it will actually run, and then your file will be moved. So I have a demo for this. Let me share my VM. Ooh. Let me restart. Okay, hopefully you can see my VMware. I just tried this demo like 1 hour ago in the Word, and I saved the VM, and of course it broke because I have a live demo, but luckily I had a snapshot, so hopefully this will work. So if we check we are at the USR local sharman, there is nothing here right now. And if we check the launch daemon folder, we have only the VMware launch D. So let's go to desktop, and I have a script to make this exploit. So I will do the reboot version. So this script basically will create the file that I mentioned, create the man page with all the section and so on. And it will also create a Python script which will be invoked by the launch daemon plist file. So everything should be created right now. So if we go back and check the location, we can see that we have a symlink, the what is the temp pointing to the library launch daemon comp sample load plist file. And if we list the man page location, we can see that we have a file name named with this brackets, exclamation mark, and so on. So now I will not wait a full week, but if you are an attacker like a malware, you probably will, but I will simulate now running of the weekly script. You can do this by running sudo periodic weekly, as it's running as root. We run it with sudo. Again, this will run as root on a weekly basis, but now I just emulating that point. So right now it run, and if we go back, we can see that indeed our comp sample plist was created. And if we check that, we can see that we have a comment at the beginning, then we have a plist, and then we have a comment section starting commenting out the rest of the item. Now I could reboot it, or basically just again emulating a reboot on the system. So I will just start this plist file manually. Again, as it's in the launch daemons, it will be run as root upon reboot. So we can run that. And this created a local bind shell on elite port. And if I connect it, I can see that I'm running as root right now. So is the exploit, and let me go back to my slides. So the last one to mention is bypassing oversight alerts. So oversight is a really great tool created by Patrick Fardell to monitor if your webcam or microphone is being used, and you can basically allow or block that operation. And you can also do like an instruction that always allow that tool. In that case, you will not get an alert anymore, and it will be always allowed. Now this whitelist, which is controlling the always allow application is owned by root. Oversight runs as root, and it also has like a kernel extension, and it's in a directory that you own. So actually it's in somewhere in your home folder. So you can basically delete this whitelist and create a new one. And you can whitelist your own application. So if you are like a malware and want to bypass the alerts created by oversight, you can replace this whitelist, entering your own application there, and it will just work. So at last, how we can avoid these attacks? In case of installers, use a random directory name in the temp folder, which cannot be predicted. Once it's created, because of the sticky bit, no one can delete it if the installer is running as root. But it can be pre-created if it's a fixed name. Many of the installers I saw, they do create a random string at the end of the directory names usually. So yeah, just use a random name and then you should be fine. But if you really want to stick to fixed names, then what you should do is you create the directory, set permission that only to be owned by root and no one else has any rights to that directory. Then you clean it up. So in case anyone placed a symlink, whatever there in the directory, it will be clean, and then you can start using it. And because it's owned by root, no one can touch it anymore. So this is for installer. Now, the move operation, if it's related to files, it will not follow symlink and hard links. So try the following: create a file called A, create a symlink called B pointing to A. Now, if you print out the contents of B, it will print out the contents of A. You can put contents into B and that will be redirected to A. So that's all fine. But let's create a third file, call it C. And then if you try to move C into B, where B is a symlink pointing to A, what I hoped will happen is that C will overwrite A, but what actually happens is that C will overwrite B, the symlink will be deleted, and basically that's it. And B will be overwritten by C. So this is kind of protects you. And the last thing is in Objective-C, many of the objects has a write to file operation like NSString. Write to file method will not follow symlinks or hard links. It will actually override them. So in this case, in the screen example, if my file.txt would be a symlink hard link, with this operation, it will be overwritten. So I found this to be a safe operation. And that should be pretty much it. And it's almost 6 p.m.
Yes.
Any questions?
I'm looking at the Slido feed and it's currently empty. So, kind of surprised, but I guess your explanations were entirely clear. Suppose somebody thinks of a question to ask at a later time. Where do they contact you best?
Probably on Twitter. My handle is the evil bit, so let me put that out once more.
All right. Yep.
So, yeah. Just I think my DMs should be open, or if not, then tweet, tag me, and I will get back to you.
All right, cool. Then I'm going to say thank you very much for your talk.